So now let's get into the second part of this unit review on chemical equilibria. And so this time we will discuss acids and bases. So we'll start off with an overview, then we will discuss calculating pH or concentration, mostly using an ICE table, aka an ice table, and then we will end off with titrations and buffers. So now we will begin with the overview. And so what I mean by overview is I mean that we will talk about what an acid and what a base is, the different definitions of them, Arrhenius, Bronsted-Lowry, and Lewis acids and bases, as well as what makes a strong or weak acid or base. And so the first ever conceived definition of an acid or base was by a man named Arrhenius. The Arrhenius definition of an acid is a compound or molecule that when dissolved in water releases hydrogen ions, positive hydrogen ions. And the Arrhenius definition of a base is a compound or molecule that when dissociated in water releases hydroxide ions into water. A Lewis base is a compound that donates a lone pair. As in, the acid accepts a lone pair, as in the proton, sort of, takes the lone pair from the base, because in order to have an acid-base reaction, you need to have a lone pair on the base so that the proton can bond with it. Right? And so that's how that works. And when I say strong acid or base, it means something that dissociates 100%. Meaning that, say you have hydrochloric acid, right? Hydrochloric acid, when dissolved in water, is going to dissociate 100%, meaning that there will only be hydronium ions, meaning H3O+, because there's no such thing as protons within a solution. It will automatically bond to something. And you will also have chlorine ion, and that's it. It will never go in the opposite direction. It's not an equilibrium situation. It only goes in one direction. No double arrows, just a single arrow in one direction. A weak acid or base doesn't necessarily mean it's weak. There are some that are weaker than others, but what it means is that it doesn't dissociate 100%. Anything that doesn't dissociate 100% is a weak acid or base. And that means that it does, in fact, have equilibrium tendencies, meaning that we can do ICE tables with it. So now we will discuss calculating pH or concentration, mostly using ICE tables. And so what I've written here is an example of an equilibrium reaction between a Bronsted-Lowry base and a Bronsted-Lowry acid. In this case, the acid is water because it donates a proton to ammonia, and ammonia is the proton acceptor, and so therefore it is the Bronsted-Lowry base. Over here we have the conjugate base, hydroxide, and the conjugate acid, ammonium. Meaning that in the reverse reaction, this one acts as the base and this one acts as the acid. And Kd, all that means is that it's the equilibrium constant for the base. For the base reaction. That's it. And what I mean by the base reaction is this one right here. If it were the opposite direction, it would be 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which is about 5.6 times 10 to the negative 8. So let's say that we're given the initial concentration of ammonia as 0.3 molar. Okay? And so what we do is we set up our ICE table, excluding water because water doesn't matter, because it's a liquid, and liquids and solids are not considered in an equilibrium reaction for acids and bases, or normally any other equilibrium reaction, because they don't contribute much to the equilibrium because they're solids or liquids. But also because the water is also the system in which it's taking place. the concentration of water is going to be too much for it to matter significantly. Sometimes it does matter, actually. But in this case, not so much. ICE. Ammonia. Hydroxide. Ammonia. Our initial concentration, 0.3 molar, 0, and 0. Our change, minus x, plus x, plus x. Our equilibrium concentration, 0.3 minus x molar, and x molar. Our equilibrium expression or equation, x times x, so x squared, over 0.3 minus x is equal to the kb, 1.8 times 10 to the negative 5. When we solve for x, we're solving for the hydroxide concentration, and that's important. And I'll explain to you in a little bit. But what you do is you just do what is known as the 5% rule, meaning you pretend that this x is insignificant because of the fact that it's going to be too small for it to matter. And then you just multiply both sides by 0.3, and then you take the square root, and that'll give you your x. And if that value divided by the original concentration 0.3 times 100% is less than or equal to 5 or somewhere around 5, then what you have is something that follows the 5% rule, meaning that the x does not really matter in that case. If you have something that's way more than 5%, like 10 or more, like 10% or more, then you have to do the quadratic equation. And so when I do the calculation for x, I get around 2.3 times 10 to the negative 3 molar. Okay? And if I do the 5% rule, it follows the 5% rule because of the fact that when you do the division and the multiplying by 100%, you get around 0.77%, which means that it doesn't really contribute all that much. And so this, in fact, does follow the 5% rule. And so now that we know our concentration, or our value of x, which is essentially the same thing as the concentration of hydroxide, this is important because we can calculate what is known as the POH, which is just the potential of hydroxide in the solution. And the potential of hydroxide is just the same thing as the negative log, base 10, but we don't use base, but since it's base 10, we just say negative log, of the concentration of hydroxide in the solution. And this is the same thing as 14 minus the pH. And pH being the potential of hydrogen ions or hydroxide, really. So this is the same thing as 14 minus the potential of H3O plus, right? Which is just 14 minus negative log, so plus log concentration of H3O plus. And that's it. And so if we want to find the pH, instead of the POH, all we have to do is just calculate the POH, then do 14 minus the POH. And so what is our concentration of hydroxide? It's just 2.3 times 10 to the negative 3 molar, as we had calculated, because that's equal to x, and x is the equilibrium concentration of hydroxide. And so therefore, the POH is equal to negative log of x, which is equal to the negative log of 2.3 times 10 to the negative 3 molar. Which doesn't really matter since there are no units on the pH, it's just the potential. Which is equal to around 2.7, I would say. I was close. It's actually around 2.64, and notice how I'm using 2 decimal places because that's the number of sig figs in this concentration. So the number of sig figs is the number of decimal places you will approximate the pH to. Our POH, not pH, is 2.64. The same rule applies to POH as pH, of course. No, it doesn't really matter, but I meant to say POH. Anyways, so our POH is 2.64, and so our pH is 14 minus the POH, which is just equal to 14 minus 2.64, which is equal to 11.36. And so that's our pH. And to calculate the concentration, we don't need to do this extra step of taking the negative log of the concentration. We can just use this to find the concentration and then plug it back into the equation. Say this was like 2x, right? Just multiply it by 2. Done. There you go. And that's how you calculate the pH, or the concentration, for an acid or base reaction. So now we will be discussing buffers and titrations regarding acids and bases in chemical equilibria. And so let's start off with buffers. So what is a buffer? A buffer is a solution that has both an acid and a base within it that maintains its pH when a strong acid or base is added to the solution. And so an example would be your blood. It maintains its pH because if its pH were too different, what would happen is that you would die. So it has to maintain its pH, which is around 7.4. So an example would be acetic acid. This is the symbol for acetic acid, which is actually CH3COOH. Either one works. We'll just go with this one. Plus H2O, equilibrium arrows, double arrows, yields is what that also means. CH3COO minus, meaning acetate, plus hydronium. This would be a buffer if this is in the solution and this is in the solution before it reaches equilibrium. Meaning that, say we have 0.5 molar of this and we have 0.3 molar of this. Okay? So we have 0.5 molar acetic acid and 0.3 molar acetate. Now what we can do is we can say, if we know the Ka is equal to 1.8 times 10 to the negative 5, just like with ammonia, then we can say that we can do an ICE table. Ignoring water once again, because it doesn't matter. Water doesn't contribute to this calculation. ICE. I'll just fill this out. And so the reason why I put this little squiggle in front is because this means approximately 0. And why is it not exactly 0? Well, because of the autoionization of water, which randomly happens sometimes, which means that there could be a little bit of hydronium within the solution, because water sometimes reacts with itself and has an acid-base reaction equilibrium with itself. But this happens very rarely, and so normally it's just around 0 because it's too small for it to matter. And so the change is going to be minus x from the acid, because always you're going to go, because this is the, this is the direction of the reaction. We have the acetic acid plus water first, which means that it's the reactants, meaning that we have to subtract from the reactants, because we always subtract from the reactants in the direction of the reaction. And then add x, and then our equilibrium concentration, 0.5 minus x, our equilibrium concentration x plus 0.3, and our equilibrium concentration x. Okay, and so what is our Ka expression? 1.8 times 10 to the negative 5 is equal to x times 0.3 plus x over 0.5 minus x. Okay? Again, x is going to be too small, so we can cross it out of both of these, and so we're just left with 3 over 5. X is equal to 1.8 times 10 to the negative 5. So that's about 0.6. X is equal to 1.8 times 10 to the negative 5. So that means that x is around 3 times 10 to the negative 5. 3.0. Okay? Molar. And obviously this will follow the 5% rule because we have 0.5 molar originally. So it's not going to matter too much. So what we are saying here is that our concentration of hydronium, which is 3.0 times 10 to the negative 5, which means our pH is going to be the negative log of this, 3 times 10 to the negative 5, which is just 5 plus the log of 3, which is just going to be a little bit less than 4, so around 4.6. Close again, around 4.52. And so our pH is about 4.52. But what's an easier way to calculate this without using this? Well, there's something called the Henderson-Hasselbalch equation. So we calculate our x. Our x is was 3.8 times 10 to the negative 5 molar. And then all we have to do after that is just say the pH of this buffer is equal to the pKa, meaning the potential of the acid acid constant, meaning just the negative log of 1.8 times 10 to the negative 5 in this case, plus the log of the concentration of base at equilibrium divided by the concentration of acid at equilibrium. And that's it. That's all you have to do. And so our base equilibrium concentration is just 0.3 plus this, and this one is just 0.5 minus this. And this is so small that it doesn't even contribute to the actual pH. And so therefore we don't care about it. And therefore we're just going to use our original concentrations because it doesn't change enough for it to actually impact anything. And so what we do is we say, all right, so the pH is equal to the negative log of 1.8 times 10 to the negative 5 plus the log of 0.3 over 0.5. And this gives you around 4.52. What did we say before? Oh, right, 4.52. So it hasn't changed. It's still 4.52. And so this one, you have to be careful with it. You will always get it right if you do the ICE table. But if you do the ICE table and the expression for the equilibrium constant, but if you're in a rush, this is very useful, especially if it's a very weak acid, meaning the Ka is very small and you have very high concentrations. If you have large concentrations and a small Ka, it means that the X value, meaning the equilibrium concentrations, are not going to be too much different from the original concentrations, and so therefore you don't have to worry about it. And you can just plug in the original concentrations, the Henderson-Hasselbalch equation, and therefore you will get the correct answer, at least something very close to the correct answer. And so now we will discuss titration. And so what is titration? Titration is using a strong acid or a strong base to neutralize a weak acid or a weak base, or a strong acid or a strong base, essentially to neutralize an acid or a base. So like acetic acid, right? So to neutralize this, we would use this. And what we use titration for is we use titration to calculate how much hydroxide would be needed to neutralize a complete solution, or some solution, or some concentration of an acid or a base in this reaction. And so here we're titrating something with hydroxide, meaning this is an acid. And so it starts off around here. So I would say this is around 2. And then ends off around here, which is around 12. Okay? And this point, this middle point, this is called the equivalence point, where the moles of hydroxide are equal to the moles of acid. Okay? So what is this acid? Well, because the equivalence point is at 7, it has to be a strong acid. It has to be a strong acid. That's the definition of a strong acid. Because, right, this will yield only, because HCl is a strong acid, H2O and Cl minus. Cl minus is a neutral ion because it comes from a strong acid. A strong acid has a very weak conjugate pair for a base, and therefore that means that this is neutral, so it does not contribute, so it doesn't go in the opposite direction. Which means that all you have are neutral compounds or molecules in your solution once it's been completely neutralized. By the way, all you have to do here is just stoichiometry and then the Henderson Hasselbalch until you reach the the equivalence point. When you reach the equivalence point, you have to do the reverse reaction, meaning you have to do like H2O plus Cl minus. Or what you can do is you can calculate what the halfway point is if you're, some sort of math genius. But what I would like to do is say we have our acid plus our OH minus, and this yields our base plus water. Right? And so to calculate what pH the equivalence point will take place at, we just use the reverse reaction. A minus plus water yields the acid plus OH minus. And this will give you the POH, because OH minus, and then you can just use the POH to find the pH. And then that's it. And so now that we're done with acids and bases, I will see you in the next video in which we will discuss solubility as it relates to chemical equilibria.